If we try to solve a congruence of the form x to the n congruent to a mod n, it's possible we can find a k so that nk is congruent to 1 mod phi of n. In that case, we can compute a solution directly as x congruent to a to the k. But if the greatest common divisor of our exponent and phi of n isn't 1, this won't be possible. We could use trial and error, but can we make our trial and error easier? If the modulus is composite, the Chinese remainder theorem does give us a way to simplify the problem. Let f be a polynomial, and suppose we want to solve f of x congruent to c mod pq, where p and q are relatively prime. We can find a solution to f of x congruent to c mod p and f of x congruent to c mod q, which will solve the original congruence. For example, let's solve x cubed congruent to 33 mod 40. So factoring 40 as a product of relatively prime numbers, we want to solve the simultaneous congruences x cubed congruent to 3 mod 5 and x cubed congruent to 33 mod 8. And first, note that we can reduce both congruences. We still need trial and error, but since our moduli are smaller, we don't have to try as many values. We find x cubed congruent to 3 mod 5 if x is congruent to 2, and x cubed is congruent to 1 mod 8 if x is congruent to 1. Then, by the Chinese remainder theorem, x congruent to 2 mod 5, x congruent to 1 mod 8 has a solution mod 40, which will be x equals 17. Now, you should be a little suspicious that we pulled a fast one. After all, the Chinese remainder theorem went from a linear congruence to another linear congruence. However, the fact that we're using powers doesn't alter the results. So let's walk our way through that. Suppose x is congruent to 2 mod 5 and 1 mod 8. Then if I cube them, I do get x cubed congruent to 3 mod 5 and 1 mod 8, and if that's true, x cubed is definitely congruent to 33 mod 40. What's important to realize here is it doesn't matter that we have x cubes here. Nothing changes if we use another variable like y. Or, using the actual numbers, we found the least positive solution to our system of congruences is 17, and we can verify 17 cubed is congruent to 3 and to 1, but y congruent to 3 mod 5, congruent to 1 mod 8, has a unique solution 33, and so 17 cubed must be 33 mod 40. Now, there is one important thing to note here. Note that while 17 is the least positive solution to our two congruences, which make our cubes correct, and 17 is the unique solution, mod 40, to our congruences, this does not mean that 17 is the unique solution to our cubics. There could be other numbers congruent to 17 mod 40. For example, let's try to solve x cubed congruent to 17 mod 36. We factor 36 into a product of relatively prime numbers 4 and 9, and then we split this into reducing. Solving x cubed congruent to 1 mod 4 gives us x congruent to 1. Solving x cubed congruent to 8 mod 9 actually gives us 3 solutions: 2, 5, and 8. And what this means is that x will be a solution to x congruent to 1 mod 4 and x congruent to b mod 9, where b is one of these numbers. To find all solutions, we need to solve all cases. So let's solve x congruent to 1 mod 4 and 2 mod 9. That gives us x equal to 29. If x is congruent to 1 and 5, we have solution 5. And if x is congruent to 1 and 8, our solution is 17.